Gradient iterated temporal difference learning. I bet that as soon as you see this slide, you recognize the Atari benchmark and the Mujoko simulator. You might already think about using an Atari agent to control the Atari benchmark, and you might thinking about using SAC to control the Mujoko simulator. There has actually been a lot of work built on top of those algorithms. For example, for SAC, there has been C51, Rainbow, Munchausen. For SAC, we have seen RedQ, Simba, XQC, just to name a few. They are all more and more powerful, showing different behaviors and higher performance, but they all rely on the same mechanism, which is semi-gradient TD updates. Indeed, they all try to minimize the distance between the online network, Q of SA, and the target, R plus gamma max, stop gradient of Q, which is the target network. And the stop gradient operation here is what matters. But unfortunately, those methods are known to be diverging. Indeed, in 1995, Barrett introduced an MDP, which is called the star problem, for which the value error of TD learning grows as the number of training steps increases. But it doesn't have to be that way. Gradient TD methods, such as TDRC, actually exhibit a converging behavior, where the value error goes down as the number of training steps increases. This is because those methods are not using semi-gradient updates. They are kicking out the use of stop gradient operation. Unfortunately, those methods, they can be slow to converge. In the same paper, the whole problem was introduced to show that TD learning can learn much faster than gradient TD methods. So in this paper, we investigate the question of designing an algorithm that is fast, but also convergent. For that, we take inspiration on a theorem that was published in 2011 by Amir Masood Faramount, for which we actually bound the distance between the optimal Q function and the Q function we have after k steps. This bound is actually quite complex, but one thing to notice is that it depends on the sum of Bellman errors that has been seen during training. So we use this term as an objective function for a new algorithm that we call gradient iterated TD learning. The good news is that gradient TD learning, iterated TD learning converges. This is because the loss only depend on its parameters. And indeed, in the birds counterexample, GITD converges. One thing that is interesting is that it's also learning faster than TDRC on the whole problem, as we can see on this figure. This curve, the blue curve, is lower than the purple curve. So this was enough to convince us that we should try on larger benchmarks. So for that, we used 10 Atari games in the online discrete control setting, 6 Mujoko environments for the online continuous setting, and 10 Atari games on the offline discrete control setting. Each time, we report the IQM return as a function of the number of iterations that we take with the environment. We also report the area under the curve of each method. We selected a baseline for each specific setting, and we evaluated it. Then we evaluated its gradient TD counterpart using TDRC as a method of gradient TD updates. And we see that it performs worse in online setting, but actually quite a bit better already in an offline setting. Then we used a baseline that I will not explain here. And finally, we evaluated our method, gradient iterated temporal difference learning, which actually outperformed all the other considered algorithms. So we concluded that GITD performs well in deep RL benchmarks. The main takeaway of this paper is to say that gradient TD methods can work well in deep RL. And gradient iterated TD learning is one example, for which we minimize the sum of Bellman updates or Bellman errors that were incurred during training. There, the Bellman operator is noted gamma, which is the expected reward plus gamma the next estimate. Thank you.